This is part 3 of our Introduction to Electrochemistry and Electrochemical Cells. And in the last part 2, we were looking at these two reduction half reactions. And I was talking about how for a galvanic cell to be spontaneous, galvanic cells are always spontaneous redox reactions, when you add your cell potentials together, you have to get a positive number. One of your half reactions will always be a oxidation, and the other will always be a reduction half reaction as well. We're going to talk about how to do these calculations in just a second. So the less positive, or another way of saying that, the more negative reduction potential is going to need to be flipped around or reversed, and it's going to become your oxidation half reaction. You've got to make sure when you add the two together, one is an oxidation, one is a reduction, and you have to make sure that when you add them together, you get a positive cell potential. So whenever you reverse it, the reaction, and write it as an oxidation half reaction, this also reverses the sign of E. So if the cell potential was negative, then when you flip the reaction, it flips the sign of delta E. So from the table of reduction potentials, we have to flip the zinc half reaction in order to get those to give us a positive cell potential. So we flip the reaction, and we therefore change the sign to positive. And then for copper, we leave it as a reduction. So this is now an oxidation, and this is our reduction half reaction. Now, notice that when you add these together, you're going to definitely get a positive cell potential. We get a positive 1.10 volts of electricity that will flow. Now, what you do now is make sure that your electrons cancel out. Now, these happen to be equal. Remember back from when we balanced redox reactions, before you add your half reactions together, your electrons have to cancel. So these do. If they did not, you would have to multiply the half reactions to get them to cancel. These two cancel here, here. So now you bring down the rest. Copper 2 ion plus the zinc metal yields zinc 2 ion plus the copper metal. So this would be your balanced redox reaction that is taking place in the electrochemical cell, and your cell potential is positive 1.10, and this is spontaneous because you've got a positive cell potential. Now, when we calculate delta G with the first equation, you will find the delta G for this will be a negative number. And delta G, if it's ever negative, your free energy, then that also indicates spontaneity of the process. Now, let's talk about a shorthand notation that we use, which is called line notation. That same electrochemical cell, considering that, the one I have here, an abbreviated or condensed way to represent the electrochemical cell is by using line notation. So basically what you do, you'll notice I do have lines here, but the way you separate it all out is you from your anode half cell, this is from your anode. Anode is going to be written first, and then your cathode is going to be written second. The double parallel lines here represents your salt bridge. And the order that you write these in, if you look back at your redox reaction, you're going to put the electrodes always go on the outside. So the solid zinc is on the outside here, and the solid copper is on the outside here. I think of it kind of like a sandwich. Like these are about to be the pieces of bread, and the ions are like the meat in the middle, if you want to think of it that way. But you always have your solid electrode, your anode electrode, and then you do one vertical line, and that represents the phase boundary between the metal. Okay, so this metal surface here, the phase boundary between that metal and the liquid in solution. Okay, and then you put your ion, because what's happening is you have those zinc ions. If you think back to the video, the zinc ions are in solution. And then you put your double parallel lines, which represents your salt bridge. And then you put the copper ion, these are the ions floating around in solution here that are going to be migrating to the cathode. And then you put your metal electrode last. This is your copper electrode, the metal itself. So you put the anode material a vertical line that represents your phase boundary between the solution and the metal. Then you put your anode solution, the ion that's in solution specifically. Then you have your salt bridge, double parallel lines, cathode solution, and then the cathode material. That is how you interpret the line notation. Now, the way that we calculate delta G for these electrochemical cells is we use the formula delta G at standard conditions is equal to negative N, which stands for your moles of electrons, F, which is Faraday's constant, and here's your cell potential that we just looked at on the last example. This is known as the Nernst equation. N stands for the moles of electrons in the balanced redox equation. F stands for Faraday's constant, and this is always a constant, 96,485 coulombs per mole of electrons. That's a coulomb. That's not a temperature in Celsius. That's coulombs per mole of electrons. So if you go back to that copper and zinc reaction we were looking at with the electrochemical cell example, remember from that we got a positive 1.10 for our volts. So when you plug that into the Nernst equation, you see there were 2 moles of electrons that canceled. So the 2 moles of electrons, plug in for the N, because N stands for the moles of the electrons. Plug in Faraday's constant, and then you plug in your cell potential. Now, one thing that's important to note is that this is a conversion factor you need to memorize, that 1 volt is equal to 1 joule per coulomb. We will use that in some of our calculations. You need to memorize this. All right, so notice your coulombs cancel with your coulomb. Notice that the mole of electrons cancels with moles of electrons. So the only unit remaining is joules. So when you plug all that in, you get negative 212,267 joules. And we typically want to express our free energy in kilojoules. So that would be negative 212 kilojoules. And again, that's negative, so it's spontaneous. If your delta G is negative, we know we have a spontaneous process. That is it for the Nernst equation and how to calculate delta G. We will do some more of these calculations in class.